All right, thank you very much, Seth, and welcome everyone to another exciting session of our monthly office hour program. And as Seth said, I am Mac Ilterhuni, and I'm excited to be presenting to you today about one of my favorite topics and one of my favorite modules within the ENERCALC's library of diverse and extensive modules. Without further ado, let's start. And we are going to start today by just taking a brief overview of the overall agenda. We will be talking about ENERCALC's latest build, what's new in ENERCALC, and of course, composite steel beam design, and how to register for office hours so you get notified in the future. And last but not least, we will open this up to live Q&A. So please feel free to drop your questions in the Q&A form throughout the presentation. First, I'd like to encourage all of you to check your software to make sure that you are on the latest build of ENERCALC. And the way to do that is by, if you open your software, you will see your current build at the top of the program. We do release monthly updates, and we want to make sure that our users are taking advantage of the newest features and latest updates and program capabilities. We commonly receive support questions from our users where they might have an issue or their calculations might not match the program output. And very often, these issues are resolved by identifying that the user is an old build of the software. And as soon as they update to the latest build, a lot of their issues are resolved. So we're going to go take a quick look and show you how to update your build and get notifications for new builds so you can stay up to date. So at the very top right side of the program, there is an update button in that ribbon bar, and if you click on that, this window will pop up, and you will be able to check for updates by launching the For Our User page, and you can download the latest build from there. So if you launch the For Our Users page, you can install the latest build update under the software download section. And once this file has been downloaded, you can launch it and you'll be running the latest and greatest build of ENERCALC. Very simple and quick process. And if you would like the program, and I recommend to make sure that the program automatically checks for these updates for you at the program startup, you can simply instruct it to do so by selecting this by checking this box at the very bottom, which is this box right here. So the current build that ENERCALC is on right now is 2025 to 0204, which is the February 4th release. And some of our users, and this is a quick note for some of our users who are stuck in this set of builds. So if your build is in between 2023 0830 all the way to 2024 0828, if your program is on that build, then unfortunately the feature to automatically notify you of the availability of new updates is not functioning properly. And for you to be able to fix this, you will have to do one manual update from either, again, inside of ENERCALC or from the website, just like the way we went through it right now. But that would require you to do it just one time manually. Then after that, it'll be a quick automatic process. If you prefer to be notified of the latest ENERCALC updates by email, you can scan this QR code here on the left, or you can just go to this website, enercalc.com, or this webpage, enercalc.com/update-emails, and you'll have to fill in your contact information so you can receive information via email. Now, if you have not been on the latest build, or maybe you haven't had the time to poke around ENERCALC recently, we want to highlight some of the new features and functions that we hope you can take advantage of. The first one is the decoupling of IBC and ASCE editions. Some jurisdictions have started mixing and matching design standards. So, for example, a jurisdiction might be using IBC 2015, but it wants you to use ASCE 716. So these are not, as you know, IBC 2015 references ASCE 710. So the standards here are not matching the referenced code. So previously we used to have everything lumped up together. So you'll have the IBC edition is lumped up with all of the other standards based on whatever edition they reference. So IBC 2015, it'll have the NDS 2015, it'll have the ACI 2014, and of course, ASCE 710. But now what you can do after we decouple these options, now you can actually select an IBC that doesn't match an ASCE. So you can do IBC 2015 and ASCE 716 or 722. And this will allow you to have a greater flexibility in meeting the jurisdiction's requirements. The second update is the addition of new ASCE 7 2022 modules. And I'm sure y'all have noticed that we started adding 3 new tabs to the calculation menu. The first tab is the seismic loads tab, and right now we have added calculation modules for seismic base shear, seismic wall anchorage, and seismic demands on non-structural components. The next tab that we added is the wind loads tab, and we added a calculation for the ASCE 722 wind forces per chapter 27 and chapter 28, and we also have a calculator for wind enclosure. So currently under active development, we have the component and cladding module, which is chapter 30 for ASCE 722. That's being actively developed, and once it's released, it will be housed right here under the same tab. So stay tuned and keep your eye on future updates. The last tab we have is the other loads tab, and right now we have the ASCE 722 live load reduction module, and recently we added the ASCE 722 snow loads module as well. And of course, another exciting update that's been going on for a few months now, but we're surprised by how many people still don't know about it, which is the native load linking within ENERCALC. Load linking gives the user the ability to automatically link reactions from one calculation to another, and the ability to change something in one member or change loads in one member, and then have the effects of that change trickle down to all of the supporting members downstream. So this was one of our most requested features from our users, and we're excited to say that load linking for steel beams is here and ready for you to use. Load linking for other modules is in active development, and we want to make sure that you stay up to date with the latest build. So this way you are taking advantage of these features as soon as they roll out. So now let's briefly just talk about load linking, just to refresh everyone's memory in case you've seen it before, and of course introduce it to our new users. So if you're on the latest build, you'll be able to see a new tab on the top called Calc Order, and this tab organizes all of your calculations based on the load path order. So you have a quick overview of the calculations that are linked together and in the proper load path order. You can link multiple reactions from multiple members at the same time, and ENERCALC understands the load path logic, and it ensures that all the calculations are performed in that load path order. And at the bottom, we have added new load linking status badges. These badges help you navigate the status of each calculation and understand the warnings a little bit better. So for example, if we were to update the loads in beam 1 right here, we would see the linked load status badges on the downstream members like the primary girder and the transfer girder and so forth. You will see those status badges actually changing from from green as shown here to either orange or red to signify that you need to do a recalc and signifies some other relevant information. And at the very top here, we have a new button called Recalculate Linked Loads. And this button allows you to bulk recalculate all of your calculations to ensure that the most up-to-date reactions are being used and their effects are indeed trickling down to all the members, or all the related members downstream. So if you jump into any steel beam calculation module right now, you'll be able to see a new tab called linked loads. It's tab right here. And in this tab, you can grab reactions from whatever calculation you have in the ENERCALC project file, and you apply them to the beam. And you can even, this is all of the other calculations that were created in that same project file. And you can cycle through these calculations, and you'll have the 2D diagram here on the right-hand side change as you select the different calculation, because the diagram is a true reflection of each calculation, and this will help refresh your memory just to make sure that you have the confidence that you are picking the correct calculation to grab reactions from. So for example, you can choose to apply linked loads. Once you grab a reaction, you can choose to apply those as linked loads based on whatever location or spacing you want. You can apply them at mid-span, third points. You can apply them at very specific location, maybe 3 feet from the left. You can do whatever you want here. Once these loads are applied, they will show up on your beam as or color coded in blue, and that signifies that they are linked and not applied, manually from within the same calculation, aka by using the span loads tab. So overall, load linking is a powerful tool that allows the engineers to create a well-connected chain of calculations while minimizing the risk of transcription errors. If you'd like to learn more about load linking, or if you need more information, please check out the load linking playlist on our YouTube channel. This playlist will walk you through how to use load linking step by step so you can start leveraging this powerful tool in your projects. The final new feature we wanted to highlight today is our ENERCALC for Revit, a gravity full load path. And ENERCALC for Revit is a Revit plugin that allows you to design structural members fully within Revit without having to export information to another calculation software. It's a very simple point and click workflow that allows you to design a member in a fraction of the time it would take otherwise. So we previously supported steel beams, steel composite beams, wood beams, and girders. And recently we started supporting columns and spread footings. And this way you truly have a full gravity load path from the roof or the floor all the way down to your foundation design. So moving on to the focus of our session today, and that is the design of composite steel beams using the composite steel beam module in ENERCALC. So we'll cover the module's engineering capabilities by walking through an example together. So here's a quick overview of the capabilities and the features of the composite steel beam module. The first thing that it can do, or the first thing that it can do, is that, of course, it can analyze and design shored and unshored composite steel beams. It supports, solid slabs as well as slab on metal deck composite beam design, and it does full composites. It also allows you to pick the option to say, hey, I just want the minimum number of studs, or a user input composite percentage for greater level of flexibility. If your firm has maybe a minimum percentage that they like to use, for example, they say, hey, nothing less than 50% composite. We're not going to do anything less than that, or nothing less than 75%, or so forth. So you'll have the ability to do that. You can, of course, analyze pre-composite and post-composite states for the unshored design, which is extremely critical. And then calculate deflections using the sections moment of inertia as well as the lower bound moment of inertia for accurate deflection calculations based on when the load is actually applied, whether it's a pre-composite or post-composite loading. So to put this in the right framework, we're going to go through a realistic example here. So in today's example, we need to design a composite beam system with 3-inch normal weight concrete over over a 2-inch Volcraft, 2 VLI metal deck. This is a very common assembly. And we're going to assume that the deck is perpendicular to the beam. And this will give us a total assembly thickness or total slab thickness of 5 inches, 3 plus 2. Next, we have an effective width for the composite beam of 6 feet, and we need to do unshored design. We have a beam span of 24 feet and beam spacing of 8 feet. So this means the trip width is 8 feet for our beam. And then we need to design the beam for pre-composite loads that will be removed before curing of the concrete, meaning the load is not permanent. This is for our purposes, we're going to consider this a construction load of 20 live and 20 dead. Then we need to also design the beam for a permanent post-composite loads of 40 PSF dead and 40 PSF live. And lastly, we want to make sure that to include the self-weight of the beam, self-weight of the slab, which will apply, of course, during the pre-composite state, as well as remain permanently applied to the assembly during the post-composite state. So to start a new composite steel beam calculation, we follow the same familiar process to start any module. So you click on the Add button, and then you navigate to the Beams tab, and then lastly click on the Composite Steel Beam module. And we're gonna start with our inputs under the General tab, and then we will work our way through the inputs, moving left to right to set up our calculations, following the other tabs like the span and section tab or span loads tab and so forth. So we start at general and move left to right. And the first thing that everyone should do is just give a unique name to your calculation. So we'll start by calling this CSB, Composite Steel Beam 1, very unique name. So we'll start there. And then the next step, we want to cover some of the basic design parameters. ENERCALC can design, of course, in both ASD and LRFD methodologies, and we will use ASD for our example. Next, we want to examine some of the basic values, such as the FY of steel. We're planning on using a W section, so we'll use 50 KSI, and of course the modules for steel is 29,000 KSI is fine. And the last item we have in this block is the maximum allowable deflection ratios. We're planning on using a L over 180 for pre-composite, L over 360 for transient loads, and L over 240 for the final post-composite state. And as we move down, so we want to give a little bit more information about the assembly itself. So since we have a 3-inch concrete over 2-inch metal deck, that means the total slab thickness is 5 inches. So we input that right here. Next, we also have to determine the effective width of this assembly. I already put that in the example statement or the problem statement, and that's 6 feet. The AISC provides a simple process to determine the effective width, and it depends on the overall framing geometry, such as the total span, the spacing of the beams, and of course, the distance to the edge of slab. So that's why this is a user input, as the software doesn't really know your overall framing plan, what that looks like, for it to be able to determine this information and auto-calculate the effective width for you. So that's why it's a user input. However, if you click on this button, you'll get this little pop-up window that will display the AISC code reference language to help you navigate the process of calculating the effective width. And as you can see right here, this is a copy-paste from the code. So this will help you, and of course shows you here the code reference where we get that information from. So you can perform that calculation on your own quickly. Next, we have the option to specify the use of a metal deck. and by checking this box right here. So slab on metal deck, you can check this box. Now, if you uncheck this box, so if we don't choose this, the calculations will be performed as if you have 5-inch solid concrete slab. The user interface will look like this. If you actually uncheck it, this will be completely gone. There will be nothing here on the right-hand side because you don't have a metal deck. And then the top right shows you here a 2D cross section of the assembly as taken from the ENERCALC 2D tap, and you can see again 5 feet, and you can see here the 6 feet for the effective width. And at the bottom right here, you can see the 3D visual of the assembly with a full depth slab over the steel beam. There's no metal deck right here. And again, both of these images or depictions are taken directly from ENERCALC. So since our example is utilizing a metal deck, then we'll just check this box. So the user will also have the option to input their own rib measurements for the deck. So right here, these are user input. You can put your own, especially if you have a maybe a historical deck that's not readily used nowadays, or something that's just different. You can always input your own information here. And if you already use a typical deck, you can just click on this button and you'll be able to access the database that the ENERCALC has, which includes many of the popular metal deck products grouped by the manufacturer over here on the left. So in the database, we already have the Volcraft 2 VLI deck, which is a very common deck. So we will just jump to it right here, and we will pick it from the list and click Use Selected. And once you click that, it will auto-populate all of the information here for you as far as the rib measurements. So now that we have specified the rib measurements and everything, now we need to actually talk a little bit about the direction of the deck. So the direction of the deck here, we have ENERCALC allows you 3 options right here. You can say if it's perpendicular to the steel beam, parallel to the steel beam, or mixed, and that's whenever you have some sort of a transition area where the deck changes directions. So if you're designing the beam where the deck is changing directions, then that would be your option to choose. And it's worth noting that all of the results, as well as the 2D and the 3D visuals in ENERCALC, update in real time as you make changes. So the 2D and the 3D visuals are an accurate depiction of the input information, and they change with you as you make changes. So to give you an idea, and this is not exclusive to the composite steel beam module. This is throughout most of not all of the modules that ENERCALC offers. But for the composite beam, since that's our focus today, so you can actually click on the perpendicular direction for the deck, and that's depicted here on the left. You can see when you click on that, you will get a 3D sketch showing the deck perpendicular to beam. That's an accurate depiction. And then you will get a 2D cross section that's showing only 3-inch concrete, because that's a 2-inch metal deck right here, and that portion is ignored for calculations. Alternatively, on the right-hand side, if you do pick the parallel, then you can see the 3D depiction is changing, and you can actually see here a whole 5-inch of concrete, because this middle section now has full depth concrete, and all of that will be included in the calculation, of course, helping your beam. So to get back to our main example, the deck is perpendicular, so we will just move forward with a perpendicular direction. Moving on, we need to determine if the construction is shored or unshored. If you pick shored, then there is no longer the need for ENERCALC to run numbers on the pre-composite state. This is because, obviously, the beam is considered to be sufficiently shored and will not experience, any issues or any loads, so we're not going to worry about that. ENERCALC will only examine the post-composite state. However, it is way more common to have unshored construction. So, and of course, our example also requires us to design the assembly as unshored and check the pre-composite state for both strength and deflection. Hence, we will click on the unshored button right here. So now we need to provide, to wrap up this assembly, now we need to provide more information regarding the studs that we're using in the composite beam. So first, you can pick whatever diameter for the stud right here from this drop-down menu. You'll have multiple options, and you can pick whatever diameter you'd like. It's very common to use just 3/4 inch diameter studs, so that's what we're using. We will skip the stud capacity, the QN, for now, and we will get back to it in just a second. Moving on to this third input, we need to, and this is a user input, which is F prime C, that's the concrete strength. I'm using 3 KSI, but the user can use whatever concrete strength they need to use. And the last item here is the concrete density. This is important for the modulus, for the concrete modulus calculation, because the calculation is based on density. So this is important a little bit here. We're using 145, which is pretty typical. 145 PCF is a typical number to use, but you can use whatever you'd like. So now let's go back to the nominal shear strength capacity per stud, which is QN, this number right here. And there are two ways to address this. The first method, or the first way to go about this, the user has the option to input their own number. So if you know what your number is, if you want to use 15 kips, 12 kips, whatever the number is, you can just input that right here. This cell is open, you can put it, and ENERCALC will perform the calculations based on a QN per stud equal to 17 or 12 or 13 or whatever user input the user put there. So whatever value you chose. Alternatively, ENERCALC can help you calculate QN. So if you click on this button right here, this one right here, this window on the left will pop up. And this pop-up window is a quick calculator for QN based on the AISC provisions. So the QN equation needs a few things. This is the equation right here. And the first thing that the QN equation needs is, of course, the area of steel, and that can be auto-calculated based on the stud diameter that we already input, which is 3/4 inches. The next item is F prime C, which is a user input. That's why I wanted to jump here to the bottom first to input this information, because we're going to be using it. So we already have that as 3 KSI, and that's F prime C. And then the modulus for the concrete, which is EC, this one, again, is calculated based on the density, and that's why we wanted to make sure that we have the proper number for the concrete density. And then, of course, the FU of the stud, the tensile strength of the stud, 65 KSI is the way to go. And that takes care of the first part of the equation. And the second part of the equation, area of steel and FU, those are there. And we have these two right here, RG and RP. And these are system configuration factors. So to understand this further, the user will need to refer to the AISC table I8.2a. And to make your life a little bit easier for the purpose of this presentation, I already brought this table right here. So the RG and the RP factors are based on so many different things, including the deck orientation, the number of studs per rib, and the rib aspect ratio. There's just a lot of different, and of course, the deck orientation. Yeah, so there's just a lot of different things for you to determine which what the factor value is for RG and RP. So another example, the deck is perpendicular. So we're looking into this side. This is for deck as parallel. This is perpendicular, and we're using one stud, or we're assuming that we're going to need only one stud per rib. So the RG factor is 1, and the RP factor is 0.6. And there is a footnote. That's the case with any reference or any code that we see nowadays. There's always a footnote, and this is no exception. There's a footnote for the RP value that could possibly increase the RP factor from 0.6 to 0.75, but we're not examining this footnote and we're not considering it, so we're just using the 0.6. And that's why you write here in the little handy calculator, we're using RG, and from the drop-down menu, I chose 1, which is the perpendicular deck, 1 stud per rib, so that's the right number, and then RP is used here as 0.6. So now that RG and RP values are selected, the calculator will automatically calculate the shear capacity per stud. And in this case, QN right here is 17.24. If all sounds good to you, you can click on the button to use the calculated QN value, this button right here, and it will auto-populate that number right here for you as an input. The last item we have, but definitely not least, that we have here on the General tab is to determine the desired composite action percentage that we want to achieve. So we can pick either full composite, or you can pick calculate minimum studs. So you let ENERCALC go through the numbers and pick the least amount of studs you need to make this work. Or you can specify a particular composite percentage that you want to achieve. And I'm going with the third option here, and I'm choosing a minimum 50% composite. So I'm just starting with a 50% composite and going to see what's going to happen. So this concludes all of the input data under the General tab, and we are ready to move forward to the next tab. The next tab is a simple one. This is the span and section data tab. This is pretty straightforward. For example, from the example statement, we know that the beam span is 24 feet, so you enter that information right here. And now we just need to pick a size for the steel beam to start from. You can select the section type from here. So if you're using a W section or an HP or whatever you'd like to use, we're planning on using a W section, and we're going to use a W12 by 22. That's the section that I'm going to start with. If you want more shapes and sizes, you can click on this lookup button right here, and you will get a pop-up window where you'll have a larger database. So you can select additional types such as C and MC, and you can of course do a user-defined section right here. So you can actually click on this and define your own section with your own geometry. And that will be used for the calculations. And of course, you can use the addition of the AISC in case if you want to go to maybe an older edition or something like that, if your size is not available in the new editions, but it's available in older editions. Either way, we're just going to stick to the W12 by 22 that we already selected. And moving on to the next tab, and this tab really has a lot to unpack. This tab is very important, especially because the sequencing of the load and when the load is applied is very critical in the calculations of unshored composite beam design. So let's start at the very top. First, the user can choose to allow ENERCALC to auto-calculate and include the self-weight of the beam, and that's this option right here. And in a separate option, the user can choose to allow ENERCALC to auto-calculate and include the self-weight of the slab. For this example, we want to enable both of these options. However, for ENERCALC to calculate the weight of the slab, it needs to know a little bit more information. Mainly, it needs to know the slab trip width. Since our beams, if you remember, they're spaced at 8 feet on center, so we will use a trip width of 8 feet. The slab weight in PCF is calculated based on the average thickness of the slab as well as the concrete density that we input, that we already input under the General tab. So for them to come up with what the slab weight in pounds per square foot, it already needs to know the slab thickness. So it goes off after the average slab thickness that we're using here and the density of the concrete that we already input. And that's how it calculated the PSF of the concrete. now we have here the process to apply loads in all of ENERCALC. Various modules is actually very similar. The user can apply point concentrated loads, fully or partially uniform distributed loads, trapezoidal loads, moment, concentrated moments, all that stuff. And the process is very simple and it's the same. But before we actually go forward with applying the loads, we need to understand this part right here. This is the new options that you will get for the composite beams versus the other modules. So you can see right here that we have three options. And to understand these options a little bit better, we will have to, or what I'm doing here is that I'm actually bringing the problem statement right here. Those are the loads that we need to apply, and we need to look into this and see how we can apply them based on, based on these selections. So the first set of loads is a pre-composite construction load. We're talking about this one right here. So this is load that is applied during the construction to the bare steel section before the concrete cures. This means before the composite action is achieved. This is just the steel beam by itself. This means that the steel section by itself needs to be strong enough to support this construction load. And also, it needs to be strong enough to support the self-weight of the slab while it's wet and the self-weight of the beam. All of that load is taking place very early on before any composite action is achieved. So the steel beam needs to be strong enough to handle all of this. And not just from a strength perspective, but also from a deflection perspective, because we have an L over 180 limit, and we want to make sure that to examine the beam for that deflection limit. So for this case, ENERCALC provides two options, which these two options right here. The first option is load applied to the pre-composite section, and we already know that. That means just apply to the bare steel, but it's removed before curing. So this load is not going to stay there forever. The second part, this load is applied to the pre-composite section. So that means it's applied during construction. It's applied early on to the bare steel beam by itself. And then it's staying long after the concrete cures and after the composite action and all that stuff. That load is still going to be there. In our case, this load right here is the construction load, and it will be removed before curing. Then that is the first part right here. That's where it should be. Now, to give you a good example of loads that apply to pre-composite and then remaining forever, that would be the self-weight of the slab and the self-weight of the assembly. That's going to be there on day one, and that's going to be there forever. So if I'm applying a load that is considered like self-weight or something that's going to stay there forever, after it cures, after the concrete cures, then we will put it under this part right here, or this selection. So based on the construction loads that we have in this example, again, this falls under the first line right here. So all we need to do, we click on add load, and then we click on the full uniform load, and we put 20 live and 20 dead, because that's what we need to put. And of course, we have a trip width of 8 feet, and we select this first option. The next load we have is this second one right here, and this is a post-composite final load. This is the final dead and live load, and each is equal 40 PSF. And in this case, this load doesn't even come to the beam until the beam is in its final post-composite state and the composite action is achieved. So in this case, you kind of follow a similar process. You click on add load, then you click on your type of load here, which in our case, again, it's a full uniform. We have 40 dead, 40 live, and a trip width of 8 feet. And then we're applying it as post-composite only. So this load will only go to the post-composite, be compared to the post-composite section. Lastly, at the very bottom, you can find a summary table with all of the loads that have been applied to the beam. We can quickly confirm the first load is 20 live and 20 dead, pre-composite removed. That means it'll be removed, which is a construction load, which is correct. The other one is the post-composite load, which is 40 live, 40 dead, and it's post-composite only. So this is a quick sanity check for you. The last tab, which is the load combinations tab, this is the same familiar tab across all of the ENERCALC modules. You have, strength combinations, ASD combination in this case. They could be LRFD combination if we used LRFD methodology. You have a combination for reactions, and you have combinations for deflections. This allows the user a great level of flexibility. The user can easily add, modify, or delete combinations, as well as selectively pick certain combinations to be turned on or off. So you can just say, I want to turn off this, turn off this, turn off this, and you can easily turn them off right here, by switching yes to no under the run column right here. So this is very, very typical of all ENERCALC modules. So moving on now, we have entered all of the required input data. We can check out the results. So under the summary results tab, you can practically see all of the critical stress ratios. First, of course, you have the maximum bending stress ratio right here of 0.718, and that is and that is of course less than 1, so that's good. You can see the composite percentage that we're achieving, which is 50 in this case. That's what we wanted. And you can see the maximum applied moment, as well as the allowable moment capacity. So this one right here is the post-composite allowable moment capacity, the 137. And the max applied moment is 75. And then below it, you'll be able to see the pre-composite max applied moment. That's the load that's applied pre-composite. And of course, this is the pre-composite allowable moment capacity of the section. So this is just the bare steel. That's the capacity of the steel beam by itself. And then on the top right, we have the maximum shear stress ratio, which is again less than 1. So we're good there. And lastly, we have here the deflection checks. And I think I want to dive in a little bit here to show you the different things that we do. So the first set is the total maximum deflection. This includes the deflection that occurred before the composite action has taken place, before the full composite action has been achieved. That means whatever permanent deflection occurred on the beam by itself before the composite action has been achieved, that is additive. If the load is remaining, that is such as self-weight. So that would be additive to the post-composite deflection that comes from the additional load, such as the 40 PSF live and dead. So anyways, total deflection here after everything is said and done is 1.094, and that is L over 263. So we're good here because the limit that we wanted to use is L over 240. Then we have the transient loads, and you can see here the combination that controls is live only because that's the only transient load we've applied. And this was L over 360, the limit, so we're very good here. And lastly, this is important, this is the pre-composite deflection. This is deflection of the steel beam early on whenever we put the construction loads and all that stuff early on before the composite action. And this actually is a little bit more, which is 1.21 inches, but it's L over 236, and we wanted to achieve L over 180. So we're good here as far as our example goes. And a much deeper deflection analysis and incremental analysis values along the length of the beam can be found under this deflection tab right here. You can pick whatever load set or load combination you want. You can do the pre-composite total, pre-composite removed. For us, we're just gonna, for this example, if you can pick here the final composite, and this is the load case or the load combination that controls, you can get a lot of information, including incremental deflection information and other intermediate values that you can look at and use. Another useful tab is the properties tab, this one right here. You can find more intermediate values there, but one of the values that's really useful is the location of the plastic neutral axis, and based on the composite section percentage. So you have right here, if you're achieving 50% composites, then the plastic neutral axis is going to be at 11.8 from the bottom. And you can kind of scroll up and down and left and right and get a lot of information, such as, how many studs you need to achieve a particular composite action. And of course, the location of the P&A, if it's in the flange or in the web, or of course, if it's 100% composite, then it'll be in the concrete slab. So again, just a lot of granular information that would help you along the way in case you're trying to do something that's not traditional or not conventional. And the last item that we need to know here to finalize our design is the studs. So if you go to the studs tab, you'll be able to see how many studs you need. In this example, we will need 10 studs from 0 to the maximum moment. And in this case, maximum moment, of course, is going to be in the midspan. So from 0 to 12, you need 10 studs. And then from 12 to support 1, which is the end of the beam, from 12 to 24, you would need 10 studs. And it's very important here to note that based on this, we can fit 1 stud per rib. And that is great because this follows our original assumption when we determined the RG factor. Now, if we need to install more than 1 stud per rib, then the RG factor that we chose originally was not right, and we might need to change it. Like, for example, here, if you have 2 or 3 per rib, then you might need to use a different factor instead of just the one that I used. So we use 1.0, but this could be different. And this will change your QN value, your nominal shear strength per stud. And if that changes, it will reduce it, obviously, from going from 1 to a lower number. That would reduce your QN value. So if that reduces, that might reduce the number or increase the number of studs you're going to need, because now the studs are not as strong as you initially thought. So you might not need 10 studs, you might need 12 studs, 13 studs, or whatever to achieve the composite percentage that you need, or to get the whole system to work. And a good example of this is right here. This is the original one that we did using the factor of 1 and a factor of 0.6. The 0.6 is not changing. This is the one right here. This gives us 17.24. That's the number that we used. But if we need to put 2 studs per rib, then we have to use the 0.85. Then now the capacity of the stud is only 14.65. And that's, of course, a reduction. So it's just important to evaluate the results a little bit and go back and look into this as you prepare your details whenever you're detailing your results in your drawings. So overall, the final assembly we have here is 3-inch concrete over 2-inch VLI deck, which is 5 inches total thickness. We have a W12 by 22. We're achieving a 50% composite action using 20 studs, 10, of course, per half span, and the studs are 3/4 inches. And we have here to summarize, we have the allowable composite moment of 137 kip feet, and we are achieving the deflections that we wanted to achieve. And before we dive into the Q&A, I just want to briefly encourage everyone to register for the office hours program to ensure that you receive the notifications directly to your inbox. And this is a very quick process because most of the time when we send the email, it goes to an IT or an admin person and not necessarily the engineers. So if you're interested, you can register by just going to enercalc.com/office hours, or you can go to our website and just follow here, for our users, and then get support, and then office hours, and then all you have to do is just put your name. Everything else is optional. Your email is the only thing that's required, and then you can just click on remind me about the office hours session. And in the same page, you can always see what's the next session is going to be and how to stay in the loop. And at the same website, enercalc.com/office hours webpage, if you actually scroll down, you will be able to find the unedited recordings of the previous sessions, because we record all of these sessions, and you can access them there. And for us, the last session we did was the concrete beam session, which was held on January 8th. So if you missed that, you can go check it out. Otherwise, I think we are ready for our live Q&A.
All right, let's go ahead and jump into some Q&A. So we had a question about load application. Can you please just review again some of the details of load application? So, and we can hit other questions as well, but there was a request to go back through that. So Mac went over some of that, and again, that'll be included in the recording from today's session. but it's very similar to the load application process you have with all your other ENERCALC modules, except that you have the additional option to sequence your loads based on whether they're pre-composite removed, pre-composite remaining, or post-composite only. Mac, go ahead if you have any other detail you want to share
Yes,
about
that's
that.
correct. It's just because whenever you are designing a composite member and you are designing it as unshored, that means that it's, the member is not shored. Once you start putting the loads, you need to be able to distinguish what loads are applying to the member before the extra capacity is achieved. You get extra capacity from a composite action. However, you don't get it from day one. On day one, they just put a steel beam, they put a metal deck, and they start doing construction, jumping on it, bring their equipment and do all that stuff. So you want to make sure that that load is accounted for in a way that the steel beam can handle that load by itself and within a deflection allowance that everybody's okay with. You can't have, a 4-inch deflection on your beam because that's a problem. So that's why sequencing the load is important. So if your load is just a construction load that you're putting on in the very beginning, and then it will be removed, then you can classify it this way so you can examine the beam against that load. Now, if you are only concerned about a load that's not going to show up until the composite action is achieved, such as you're bringing, I don't know, your live load later. You're doing a second floor, an office building, and they're not going to bring their furniture and their people and all of that. That's not going to come until the composite action is achieved. Then that load is not going to be there until the post composite state. That's why you want to put that load to be checked against the final composite state. So sequencing the loads here is very important if you are designing unshored composite beams.
All right. Moving on to our next question here. Can ENERCALC calculate number of studs in steel deck where some of them are 2 per row and some of them have 1 per row, different stud shear capacity? So that's talking about the QN shear capacity calculation, which
Yes.
obviously differs if you've got pairs of studs versus single studs. So you can consider those individual conditions to get a single QN value, but you do not have the capability to combine row by row differing configurations that lead to different QN values. Go ahead, Mac, if you have any detail you want
No,
to share
that's
on that.
absolutely correct. Yeah, you're gonna just determine, not necessarily what's happening per rib, because now you're gonna have to separate the capacity of each stud that's located per rib. So that doesn't happen here. But what happens here is that you just say, okay, worst case scenario, I have 2 ribs or 2 studs per rib. Then I'm gonna choose the correct RG value or RG factor for it and just use that number across the board.
Yeah, and we always encourage you guys 100% if you have a use case that you would like to see incorporated in the future, absolutely don't hesitate to send that over to our support team at support@enercalc.com. That's how we track what features customers want to see, and that's how we set development priorities in the future. So always don't hesitate to send a feature request if there's a behavior that you'd like to see incorporated.
Absolutely.
And I believe there were 2 questions asked on that similar topic. All right, next question from Brian. I've asked about a camber option in the past. Any thoughts on whether this will be added in the future? So that kind of relates to my previous comment. If you've reached out in the past, then it's definitely on our radar, and it's something that our director of engineering is watching for potential interest by other users. But right now, at this time, we don't explicitly give camber design results, but we do provide deflection results, which you could use to generate camber specifications if you were needing to go in that direction.
And
Go
to
ahead,
add a little
Mac, you're
bit
kind
more
of doing
to
show
that,
and
yeah,
tell there.
to add a little bit more to that, I just want to make sure that at least everyone is aware of the deflection calculations. So if we're doing pre-composite state and you're applying load on the bare beam, then you're using the standard moment of inertia of that section. But if the load that you're applying is post-composite, then that portion of the load gets actually checked against the lower bound moment of inertia, which is of course a lot higher, and it's going to help you a lot with deflection since it considers the composite action. So at least we're there. So your composite or your deflection calculations that you're getting are pretty accurate, and as you know, as sharpening the pencil as you can get.
Yeah, I just want to quickly note we got a speaking of deflection results, we just had a couple of different questions about no results or incomplete results for the pre-composite max up-down ratios on the deflection results. So the development team was aware of a issue in a recent update that caused the summary tab to not properly report specifically pre-composite deflections. That fix has already been implemented, and it's going to come through in the next update. We usually roll. For those of you who don't know, we usually roll updates either once a month or twice a month with feature enhancements and fixes and stuff. And so that issue with the maximum up, down, and pre-composite deflection results has already been resolved, and it will be released in our next upcoming update. So keep an eye out for that, and always make sure you stay up to date.
Yeah, and to add to that, Seth, I know when that reporting problem was taking place in the summary, that
only in the summary.
You can still, yeah, it's only in the summary. Just it's not reported here, but if you look into the actual deflections, for example, the pre-composite state, those numbers are still accurate. It's just it was a matter of grabbing the maximum number from here and reporting it to that first summary sheet. So at least you can dig in and find it. It's not that it's forgetting about it. It's doing it.
Right, for sure. All right. Question from Mark. Does the auto-calculated pre-composite slab weight include extra weight to account for the pre-composite deflection? No. Any additional concrete required to deal with ponding effects or the deflection would need to be accounted for as an additional pre-composite load. So the total pre-composite load that's being applied is just what you've applied in terms of the self-weight of the beam and the dead loads. It's not automatically recursively increasing the dead load to account for the deflection in the beam, which I believe was the question. Mac, go ahead if you want to elaborate on that.
No, I think that's what he was asking about. He wasn't asking about the actual self weight of beam. So this is right here. This is the actual self weight of the slab, but it's not taking into account, you know, the wet concrete top effect.
Yeah,
which is the ponding and all that. Yeah. But whatever deflection you're getting, this is the part that I want to focus on. Whatever deflection you're getting by adding that, at least the standard self weight of slab, that deflection is actually permanent. So you'll have it in the beginning and it doesn't go away. And then once you add the other post-composite loads, it's actually additive to it. So we're at least accounting for that. But if there are any additional deflections due to ponding or wet effects of concrete, then that's not included here. Does that make sense what I'm trying to say?
Yeah, for sure. All right. A couple of questions from Mark regarding navigation from field to field. If your tab key doesn't move the cursor from field to field, you definitely want to make sure that you're running the latest version of the build. And if you're running the same latest public release that Mac was showing us today, and you still have issues with that, go ahead and reach out to the support team and see what we can do to help you with that. But always start by making sure you're running the latest build, because we definitely do a lot of fixes at routine intervals. Another question from Mark about the ISO view or the 3D view of his beam. Mac, can you just quickly show the navigation tools that you were using earlier as far as your zoom and pan, just so that everybody knows how to comfortably navigate that?
Yeah. Are you talking about the 3D? Here?
Yeah, just how you're rolling around and doing your zoom and pan in that view.
Yeah. So yeah, right here. You can see it from here. You can see it from here. You can turn around.
Yeah. So you're doing a left click to you're doing mouse wheel to zoom, and then left click.
Yeah, mouse wheel to zoom, and then you can click on the mouse wheel and just hold on to that. That will allow you to take it left and right. And then the left click, if you click on that, that'll allow you to rotate. But it's almost like a 3D rotation, because you can do this, you can do all kinds of rotation right here.
Yeah. And one final note on that, the 3D graphics
there are these wheels.
Yes. And you have a zoom wheel on the right-hand side as well. The 3D graphics have not always been a part of ENERCALC. Those were introduced in build 20, I believe, which is our latest major version build, which we moved to, I think, in 2021. But there have been occasionally reports of customers having a lot of difficulty with 3D graphics, and that usually traces back to having very, very, very antiquated graphics processor, graphics hardware, or out of date graphics drivers. It's pretty mainstream that most customers have an easy time interacting with those graphics. So if you have something specific giving you trouble, again, feel free to reach out to the support team. But it's worthwhile to make sure that there's that you're at least meeting recommendations for your graphics processor and graphics drivers are up to date. Question from Miguel. Where can I get the presentation? When is it possible to watch another practice like this with the Flitch plate beam module? So we do have an email address for anybody who's not aware. You can email officehours@enercalc.com with requests for future content that you'd like to see in an office hours session. So if you have a request on that, feel free to send that over. Mac, can you just quickly revisit for us where to go if people want to see office hours recordings?
Yes, you can go to enercalc.com/office hours, or you can even just simply go to our regular website right here, enercalc.com, for our users, get help support, and then office hours right here. Click on that, and you can scroll down. You can sign up to get notified here for all the future office hours, and we will always have the up-to-date information right here on when the next session is. So today, for example, this was saying the next session is today. This will get updated, and this is the topic, composite steel beam. You can join right here and add to your calendar. And as you scroll down, you will find all of the older office hour recordings. This is 2024 recordings right here, and 2025 recordings is this one, concrete beam. That was the one that we did in January, and soon this one that we're doing right now will be up right here next to it.
All right, perfect. So, Mac, if you feel like tackling one that's not explicitly on topic for today's session, Jay had a question about quickly showing how to link loads. Obviously, for this particular demonstration, we were doing steel composite, which doesn't include load linking yet, but it sounds like there's some interest in just quickly going through the mechanics of a load linking process, if you have some time to do that.
Yeah, that's pretty quick. So you can see my screen, right?
Absolutely.
Okay, so you click on steel beam just to start a first steel beam calculation. And I am going to call this beam 1. Let's see here as it opens. Beam 1. And I'm going to keep everything here the same. All I'm going to do is I'm going to make this 15 feet. And I'm going to put a point load of 5 kips at 7 feet. For example, that's okay. And I think that's all I need to do here. So this is the first beam. We want to create a second beam. That's where the fun starts. So this right here is beam number 2. And what I want to do, I want to, let's pick this to be 10 by 17. We'll keep it at 10 feet. And what I want to do, let me flip this to 2D. What I want to do is I want to grab a reaction from beam number 1, the one that I just created. So you can see here, I am not applying any load. I'm not touching this at all. We have a new tab right here that says linked loads. I click on this one, and once you click on this, right here you see it says from beams, and you will see a list of all of the calculations that you can grab a reaction from. Right now, this project file only has beam 1. If I created beam 1 and 2 and 3 and 4, I'll just see all of them right here, and I can even cycle through them because this is an accurate depiction 2D diagram of beam 1. You can see here, this is the point load that I applied. This is the W4 by 13, and this is the 15-foot beam that I grabbed or that I applied here. And all I need to do, I need to click on the box from the reaction box right here. I need to pick which reaction I need to bring, whether it's reaction number 1 or reaction number 2. In this case, let's bring number 1. And it asks you how you want to apply this load. I can say I want to apply it maybe at third points, or I can actually apply it at a very specific location. Maybe I want to apply it at 9 feet, and it's asking me from where, so it's from the left end of the beam. Now that I have all of this right here, I can say link load. When that load is linked, you can see it right here in this table. This is a summary table that's showing you the load, and it's showing it is 9 feet from the left side. Remember, this beam is 10 feet, so 9 from the left is actually all the way on the right. You can actually apply the same reaction again if you have it happening somewhere else, or you can apply and grab the other reaction. But let's assume that I have that same reaction applying at quarter points, or even better, I want to apply it every 2 feet. So that means, it'll be at 2, 4, 6, and 8. If I want to do this, all I need to do is just click on spacing, click on 2 right here, and click link, and you can see now all of these loads have been already applied. So you can just play with this. If you have a bunch of these, you can just play with them. And the cool thing is that if you apply your own load, let's say you want to apply 2 kips 1.5 foot from the left, or actually let's do it 1 foot so you can read it easily. You can see here in the diagram, the loads that you're manually applying are shown in red, while the loads that have been linked are shown in blue. If you're done with all of this, then you can just say, okay, sounds good, I like this, save and close. And now you're getting the new status badge right here saying that this beam is indeed up to date and is good to go. As soon as you get into an older beam, which is this one, and let's say you want to change the load to 6 kips, so then now the reaction changed, everything changed. So it automatically warns you saying that, hey, something changed upstream, and now this downstream calculation is affected. So you can, perform a bulk recalc right there, and if you have a bunch of them, it'll just go through them based on the load path order and update it for you. And the one thing for you to know is that an updated calculation doesn't mean that the steel beam is passing. So the steel beam could be passing. In this case, it is, luckily, but the beam could still be failing, and you'll see here in the design not okay, but the load is updated, because that's what the load linking is all about. Just want to make sure that the load is updated. The results are, of course, your responsibility. I hope this kind of covers the bulk of it.
Perfect. Yeah, that's perfect. So we have one last question, and I think we're going to go ahead and wrap it up. And we're not going to dive super deep on this, but it was a follow-up question regarding the finer points of how QN capacity is calculated based on the specific geometric location of the studs and so on. And I just want to kind of reinforce what we had mentioned earlier, which is the user themselves has the final say on the singular QN stud capacity that gets used in your calculation. That's a manual input that you can see right there. We do provide that pop-up that Mac is showing as an assistive feature for some standard situations that AISC lays out, where you can go ahead and get a QN capacity from specific standard conditions. If you have anything where you're going off-road calculating a special capacity for unique conditions, you can always do that via hand calc and still manually input the QN that you feel is appropriate. So that's open-ended for your discretion as an engineer when you're doing that. So with that, I think we have covered all of our questions. We're about 15 minutes after the top of the hour here. So Mac, thank you for going the extra mile on all the Q&A. Why don't you go ahead and wrap us up here with a little teaser for next month, and then we'll go ahead and wrap it up.
Yeah, absolutely. Thank you, Seth, and thank you everyone for your time today. Really appreciate you're here. And next month we will be going over the 2D frame module and how it can be used to design moment frames. So I hope you enjoyed our session today, and I hope that you join us next month on March 12th for a little bit of fun work on 2D frames.
All right. Thank you again, everybody, for being here. As always, remember to sign up if you want to be reminded. And also, you can always go see our recordings of these sessions or share them with your team for future reference. We thank you all for being here and for participating, and we'll look forward to seeing everyone next month.